So once again, apologies for the complications. So I have some technical issues, sorry. But basically now I think everything is working well. And since the time has come, we are about to start this afternoon session. So I'd like to welcome all of you here, lady and gentlemen, if I count correctly in the list of participants. There should be at least one lady with us. And we have today a mixture of different interesting topics that you can see in the program. What I'm going to do, and I'd like to do this usually because it's often a problem for a chair to read the names of all presenters correctly. So I'm well able to read the names of those participants who are of Slavic origin, but I sincerely apologize to colleagues from Turkey and other countries that I could mutilate your names. So I'd like to ask you personally to introduce yourself so that it's nothing embarrassing for anybody. We have about 15 minutes per presentation, so let me start right on with the first one, not to take your time and to give some more time for discussion. The first presentation shall be ready from Serbia by, I'm not sure, Istvan or Istvan, how do you pronounce yourself, from University in Novi Sad, if I'm right. And it's about IP device provisioning and abstraction in IoT solutions for MQTT-based protocol. So that's basically about networking, right? And about the Internet of Things. So please, it's your turn. The floor is yours.
Okay, thank you very much. Actually, you pronounced my name perfectly. So it's Istvan. So you made it right first time. So let me share my screen. Please let me know if you see my screen. Yeah, perfect. So first of all, I would like to thank you for being here. Special thanks to Darius for his great support, and also thanks to the chair for the great introduction. Let me describe you and explain you what we have done in the past and what we have achieved and what are the results we are really proud of. My name is Istvan Papp. I'm coming from the University of Technical Sciences from Novi Sad, Serbia. And with my colleagues, Roman Pavlovic and lady colleague, Marija Antic, we have developed WISE, which is an MQTT-based protocol for IP device provisioning and abstraction in IoT solutions. What was the motivation for such a work? What we have found throughout working for several years in the IoT domain is that the ecosystem is really heterogeneous. So there is no generic solution. There are some partial and niche solutions, which makes interoperability really difficult. Many of the IoT stacks are based on TCP/IP, which at first glance it sounds kind of a standard, but all the implementations are specialized for addressing specific needs, so that you have an IoT solution for monitoring or power control or different applications, but they're not able to communicate with each other. The reason for that is that the semantic layer, although the networking layer is similar, the semantic layer is totally different, and the entire IoT domain is really fragmented. That is quite frustrating both for the user, because the end users, customers, they cannot just buy devices and make them work together. But on the other hand, it's quite difficult for business participants, for vendors or service providers, because the ability to combine different solutions is really minimal. Some solutions are to introduce protocol bridges that would allow to solve the differences, but in that case, you have a huge gap in user experience. For example, in the smart home domain, if you buy smart things from Samsung and Philips Hue from Philips, you might make them work together, but you need a certain technical knowledge to do that. To overcome these constraints, in this paper, we describe a new protocol which runs on top of MQTT, which is generic, which is scalable and covers the entire life cycle of all of the connected devices. Of course, there are some existing solutions as of today, but as I said, they're really targeting some specific applications and cannot work together. There are some protocols that are widely used in home automation. They're like Zigbee, Z-Wave, BLE, or even DECT ULE, which are again targeting smart homes. They specify what the messages means, the semantics, and yet they cannot work together. On the other hand, they have some great features like mesh networking. They're really good for low power and battery powered devices, although they have low bandwidth, but that fits quite well the home automation usage. Further, the device discovery and advertisement is as of today provided by UPnP, which is again a protocol used by TCP/IP networks, but UPnP is really heavy on resources, so it's not really a good fit for low power devices, and microcontrollers like Zigbee, Z-Wave, and BLE are. MQTT and CoAP are kind of candidates for such a universal IoT protocol, but again, they're only defining the network layer and the communication layer. They are not imposing any hints on what actually the data that they carry means. So there is no semantics there. Similar to them, there are some additional protocols like 6LoWPAN, IPv6, Thread, which are getting closer to the TCP/IP world and the protocols I have mentioned in terms of home automation like Zigbee, Z-Wave, and so on. And they're really simple, suitable for embedded devices. But again, the semantics is missing. Of course, we are not the only one who saw this gap and tried to mitigate the lack of kind of a standard. So in 2019, big companies like Google, Amazon, the Zigbee Alliance, I think it's even Apple is in that consortium. They started something called CHIP. It's a connected home IP initiative that aims something similar what we do. The idea was started late 2019, like 1.5 years ago. Unfortunately, that's way still in the definition phase. So some devices using chip might come in next year. But again, although chip defines the communication and part of the semantics, but some important items from the device usage life cycle, like association and commissioning, is still missing. As a response to that, we propose our own protocol. We call it WISE, which has the following characteristics. It's quite complete. It covers all usability aspects of the connected device, from association, from communication, commissioning. So each detail is built into the protocol. It is quite abstract and generic. It allows to decouple the communication from related services. That allows that based on WISE, you can just assume the devices are there and you can build new services on top without going into the details, whether it's a ZigBee or IP or any other communication. It is lightweight. It can run on microcontrollers. It can run on servers as well. I will explain that or illustrate that later on. Complexity-wise, it's similar to ZigBee or BLE, which you know it's quite low requirements on resources. What we saw that IoT is a really fast-moving industry, so the protocol has to be future-proof, so it needs to be extendable. And by using some generic models, it will allow further and new devices to be integrated and built in, but it will be always backward compatible because we learned that in IoT, the existing installations are slightly different than in consumer electronics. It's not, we are not talking about a year or 2 or 3 years. We are talking about 5 years or 10 years of utilization. IoT systems are huge, scalable. That's also built into the protocol. It is prepared to work with some new technologies like IPv6, NB-IoT, and 5G. It is considering battery-powered devices. As of today, many sensors around us are battery-powered. Of course, it needs to be secure. So security is built into the every aspect from the commissioning and association up to the data transmission to the cloud. And of course, there are some related functions like device discovery that makes configuration easier, commissioning, field updates, backup, restore, diagnostics, and so on. There was another premise of us, which is usage of open standards. As of today, in order to have a successful initiative, you need to rely on open standards to be transparent as much as possible, and that would be, you know, one prerequisite to achieve wide adoption. On the right side, I hope you will see my pen. Yeah, great. So on the right side, I noted here kind of a protocol stack, how we built up WISE. So it's based on TCP/IP and UDP, of course, and the key higher level protocols are MQTT, which is as of today quite a lot used in IoT, HTTP for certain initial setup steps, and SSDP for discovery. I will give some more details later on about that. This is the overall architecture that is possible to achieve with WISE. We introduced some terms like WISE Hub. This is a device that can be connected to many different communication technologies like ZigBee or Z-Wave or even BLE, WISE, Modbus, whatever. And of course, it supports WISE devices as well. It can talk to them, configure them, and pass on the data from WISE devices to the cloud for further processing and services. That's possible to be done in kind of a local area, a home, one installation, a factory, or a field. But that works quite well also when those WISE devices are remote. That means that WISE is not bound to a local area. It can spread across a wide area. that would mean, for example, that you can have a device somewhere in the field, and yet through WISE protocol, it would appear as part of this installation. Further, we can cascade those hubs to build up really complex solutions with many smart devices. So one typical use case, if I need to illustrate it at home level, if you would have a smart home within your house, and then you have a meteo station somewhere, I don't know, like 100 meters from your home without the reach of Wi-Fi. And in that case, WISE will still bridge the gap.
So we have 2 minutes left.
Sorry?
Some 2 minutes more.
Oh, then I need to speed up. Thank you. The other option would be to have the hub somewhere in the cloud, and WISE is also capable to cover that. So all those WISE devices can connect to virtual hub somewhere residing in the cloud. So the typical use case would be smart cities. I will skip maybe some details about the implementation. So we are using JSON for as a message format. Then all the necessary information is put there, so we can use and utilize all the publish subscribe mechanism that MQTT provides. The communication can be both asynchronous and synchronous. And of course, we are using the topic structure provided by MQTT, and the flexibility is built in throughout the topics, so we can define logical entities and access credentials. On the other hand, on the right side, we are using something we call a device model, where a device is abstracted by services and properties. I think I will skip some steps related to the some implementation details. I think this is an interesting point, that each device is comprised from different services and related properties. And actually this allowed us to combine and to create any device we want. And this is what makes the solution future-proof. So as of today, we support many and built in many services and properties, starting from diagnostics and firmware update like temperature and so on. So by these atomic pieces, we can assemble a device which will be handled by the system and WISE protocol transparently without any additional processing. The implementation was done on some Linux devices like Raspberry Pi. The hub, actually this concentrator, the hub runs on a Linux, and it's a C++ software, while the actual devices are running on microcontrollers. So the WISE device is a much simpler, much cheaper and less complex platform. And based on this, we built several examples. We started with a light bulb, then extended to smart meter, and the latest one is a smart speaker. And all these devices are nicely communicating through the WISE hub, either it's a physical one or virtual one, to the cloud. And typical usage is like control, monitoring, automation, that's all supported. This is a picture of a test setup. I will keep it short. We did functional performance and stress tests to test the device and the hub, and we found that all the operations are handled quickly, so it's efficient. As you can see, the message processing time is like 14 milliseconds. The association is half a second, which is even faster than with Zigbee and Z-Wave. And of course, function-wise, we were able to have really good user experience and high level of interactivity. So just to summarize the work, so the motivation was to come up with a generic protocol that will solve all the hurdles and issues we were facing in the past 5 years related to the IoT protocols. We came up with the concept and we experimentally proved it and tested it on different platforms. And I'm happy to say that we already have some early adopters from the industry, both for the smart city and the smart devices domain. And I really hope that this wise will be attractive enough to other vendors as well, so that one day we can make standard out of it. Thanks for your time. Sorry for being late.
Thank you for your presentation. I think it's interesting. And I guess we can afford some 2 questions. Okay. Please, gentlemen, if there is a question, just tell us or raise your hand. I'd like to ask personally, because this is something also interesting for myself, the documentation about your, let's say, research and project is available somewhere on GitHub or by your university website, or through which resource? Because I'd like to share this with my colleagues, and perhaps there might be a fruitful cooperation for the future.
So it's not publicly available. Actually, so far what he has shared is with some potential partners is the description of the WISE protocol and the system. So we have some documentation available, so we can follow up after. I can leave my credentials. We can follow up to discuss and share some further information.
Okay, thank you. Any other questions, please, gentlemen? If not, then thank you very much. Please stop sharing your screen at this moment. And I'd like to invite the second speaker. And this time I'd like you to introduce yourself. Really, we are now jumping from Internet of Things to medical technologies and to healthcare. And the second paper is about fuzzy logic and neural networks in the services of melanoma diagnosis. So please, Fikret, do I read it correctly? It's your turn, please.
Thank you. Thank you. I got it. Thank you all. Thanks to Darius and Chair for their contribution to this conference and making it available for all of us. My topic is, as you said, it's medical application. We try to figure out a hybrid melanoma diagnosis system. The early detection of melanoma is a very critical issue. The first aim was actually to define what is the early detection, to define if it's possible, but through the literature we found that it's very difficult to define, because there is a lot information there, and to make a concrete and standard definition is not possible, nearly is not possible. That's why we actually evolved our intention to a hybrid mechanism, if it's possible, based on either hardware design or algorithmic based approaches. Due to that, we saw that the computer-aided diagnosis systems are already there, and there must be something new. Then we found that these neural network machine learning based new systems, CNN and deep learning, is quite powerful candidates to attack this issue. That's why we actually concentrated on different algorithms used or networks used within the CNN and deep learning, because these new techniques, especially CNN and deep learning, make it possible to detect as early as possible with the conventional methods, and then we saw that although CNN and deep learning methods are quite powerful, but there is another issue standing there and waiting for us. It was the medical grade data, to find medical grade data and big data. That was another issue, another big issue within the system.
Sorry for the interruption. Maybe it would be better if you switch your PowerPoint to presentation mode by pressing.
Okay, well, okay, I just want to gain time. Okay, you are right. So we just went through the new methods, and we tried to find whether we could be able to by using these new techniques, whether it will be possible to get new information which is hidden within the images which are available worldwide. You can see on the internet everywhere, but to find out the information, the required information related to the melanoma diagnosis is not easy, because there is a huge scientific research within this area, and it's very difficult to get a new part of information from it. So what we concentrated on the pixels and their contribution to the color and the shape of the images through CNN. To do that, we try to measure the pixel size and pixel values, and their relationship with their neighbors. What's the neighboring pixels are contributing to the, let's say, central pixels and to other consecutive pixels. That's why we found a new, actually we designed a new architecture. I hope you can follow my my computer. Now I'm pointing to the normal image. We put this image to four preprocessing techniques. We named them as compact M matrix, distance vector, pixel intensity matrix, and covariance matrix. So you have a normal image, you preprocess the image through these four new mathematics-based and software-based mathematics, and you get you get new information hidden within the image you already have, the normal image. And then when we gave this preprocessed normal image to a fuzzy logic system, we found the image has changed. Then we gave this changed image to the AlexNet, which is a powerful, to the original AlexNet, to the first contributor to original AlexNet, and by changing the structure of the AlexNet itself, we were able to detect whether the given image is a melanoma or a benign one, non-melanoma one. This was this goes through consecutive steps. This is the main contribution we think we made. The normal image was pre-processed by 4 techniques, 4 new software-based techniques, and then the image was given to fuzzy logic, and the fuzzy logic has 4 inputs and 1 output, and then these 4 inputs were defined, were limited within their own limits and rules. I think, if I not wrongly remember, we used 87 or 97 different rules for fuzzy logic, and then the new image was obtained, and then that was given to the AlexNet, but we changed the structure of the AlexNet a bit, and then AlexNet was able to detect whether the given image is a melanoma carrying lesion or a safe, or not a safe one. This is the fuzzy logic system we used. The detail is given in the paper, which is published in the current issue of Electrical and Electrotechnica. So the result we obtained was that. And the original AlexNet gave 0.5 sensitivity, 0.87 specificity, and 0.77 accuracy. But having integrated the AlexNet with the fuzzy logic we developed, we found a bit better results, partially better results, and that was due to the integration of AlexNet with fuzzy logic, because we think it's a good research area for innovative new methods if we could combine the fuzzy logic with AlexNet and other networks, which there are a lot of successful networks there. Then it could be possible to get better results. And the system developed was capable of extracting the hidden data in the pixels and the neighboring environment with the sensitivity, specificity, and accuracy values given in the previous slide. And our publication, our paper was published in Electronica and Electrotechnica. Thanks for this as well. And I think this that's all I could say. Thank you.
Thank you very much. Are there questions, please, gentlemen? Well, I cannot see anybody raising a hand or raising a voice. Let me ask again, please, because that's also an interesting topic and also possibly touching everyone. I'd like to know whether you have been training your system or, well, testing your system with just images taken from databases, or if you have performed also a clinical study with some real patients and real samples of pictures.
Thank you very much. This is a very interesting question, actually. That is our next intention. We are cooperating with our medical school, and but as you know, to gain time, I didn't mention about this point. The medical grade data is very time consuming and expensive to get it. You need to follow each patient during months or years of time. And that's why this paper was based on the available data on the internet, the ISIS data, which is used on international image processing competitions. But our next step is exactly what you suggested and asked. We are coordinating with medical school, and we hope we will get a bit a reasonable amount of patient data, and we could clinically try to see whether the network we developed is actually contributing to the patient's life or not.
Yes. What I'm also curious about, this is also a question of, let's say, obviously there are apparent consequences for telemedicine applications and medical care remotely, like now in lockdown time. It was very important for many people to examine themselves, as they couldn't see a doctor at any moment as they would wish normally. But the other question is how precise the pictures taken have to be. Again, the consequences with telemedicine. Is it satisfactory to take just your cell phone, for example, take a picture with your smartphone, focusing on the spot, or is it necessary to comply with some strict measures and strict standards to have the picture examined or tested this way?
And as you know, there are conventional methods which is quite successfully have been used to detect melanoma, but their success rate is greatly depend on the medical experts lifespan in medical science. So their experience is the crucial point in conventional techniques. If you want to use the conventional techniques to detect whether a spot is melanoma or not, its success rate is around 85 or 87%. So there is a huge number there which must be tackled, because it's human life, and 1% is too much. As one medical professor told me, 1% is one life. So for medical illnesses or for healthcare, 1% is very big. Actually, its sentence was 1% is 100%, because it's a life. So we should be careful about this point. But after the data, since the collection of the data is very difficult and expensive, then researchers and other experts, they try to find different methods. That's one of the important. That's why conventional neural network and deep learning was attracting great attention, because they these techniques are able to detect the the method, the detective melanoma or non-melanoma case, if the situation is already there, if the situation is melanoma and the conventional methods are not able to detect this illness, but but the neural network and fuzzy logic based and CNN based, deep learning based methods are quite powerful to detect this. Their success rate nowadays is around 84, 85, 86%, which means that there is at least 6% or 4% there, which is awaiting new techniques, new methods to be developed. But the core issue, the core difficulty is medical data. That is why people are trying to produce, if you like, a sort of artificial data based on the real data you got from the patient. You got an image from a patient which is melanoma by twisting this image, by giving different level of light and taking the pictures of the image, by rotating of the image. You augment you increase the number of image you have. You actually they get let's say 100 real images from the patient, but through different algorithms and methods, they produce 100 or 10,000 or more than new images. By using those images, then it became possible that based on real image, if you are able to create a medical grade image, then it helps to find the patient with melanoma, which were not available to be detected by conventional methods.
I see. Well, it would be certainly a long discussion about that. So thank you for the moment. Once again, gentlemen, any other questions concerning this topic, please? Well, if not, I'd like to thank you once again. Please stop sharing your screen. And we will give the floor to the third paper, which is again about networking technologies.
Thank you very much.
As I can see, thank you very much. As I can see, Emmanuel has now switched the camera on, so we do not have to hesitate if he's in Brussels or in Riga. So please let us go ahead with the wireless networking. And Emmanuel, please, it's your turn.
Hi, thank you. Just let me start to share my screen. Okay, can you see the presentation now?
Yes, perfectly. Please go ahead.
Okay, thank you. Hi, my name is Emmanuel, and today I come to present the paper that I wrote in collaboration with Dr. Ingrida, and it's about, well, it's improved restricted access window mechanisms for IEEE 802.11ah performance optimization. So, as we saw earlier today, the IoT world or the IoT implementations are growing so fast, actually referring to the forecast made by Ericsson in its mobility report released in 2017. There will be around 29 billion of IoT devices connected by the next year. So it's an increasing market, it's increasing really, really fast. And this market needs an improvement or in the network connectivity for the standards. Every day, the standards need to improve on some different areas. Some examples are that they should cover like wide areas. Wider areas, they should also be low power consumption standards, and also they should remain the transmission quality in terms of data rate. I would like to briefly go to some specification about the standard that here on the table, we have some comparison between non-IP and IP network standards, some of the most common standard used now for the IoT networking. So on the left side, we have the Bluetooth in the latest version, and on the right side, the opposite side, we have the LoRaWAN that it's an IP standard. Right in the middle, I have the specifications for the AH standard, which it works under the sub 1 GHz frequency band. It can support from 1 up to 16 MHz for channel bandwidth. It is a low power consumption, and a single access point can support up to 8,000 stations communicating at the same time. Regarding the data rate, depends on the configuration of the standard. It can support up to nearly 8 megabits per second. And the coverage area that can reach it's almost 1 kilometer. Even that I mentioned that the standard can support different or a wide area, a wide range of channel bandwidth from 1 up to 16 megahertz. There are some limitations and regulations in the regions. Here I have an example of the USA, Europe, and Japan. If you see the common channel bandwidth for all regions, it's only 1 megahertz, even when the standard can work with a higher channel bandwidth. Now, I would like to go a bit deeper in the MAC layer of the standard, because this layer has the two most important mechanisms for this standard. So first, at the left side, we have the traffic indication map mechanism, which is basically a hierarchical scheme where all the stations are subdivided in small groups and every station is identified by an ID. So then at the right side, I have the scheme of the restricted access windows mechanism, which is basically a mechanism to restrict the access, the communication from the stations to the access point or to content for the channel based on the ID assigned by the team mechanism before. For the raw mechanism, we can find a subdivision by a slot. It means like even when the stations are already grouped, they are subdivided in a slot, so only one station can communicate to the access point at that specific time. Well, this communication of the row groups, it's boundary by this Bacon RPS that is basically some flags to indicate the station that they can start communication with the access point. So the problem statement for our research is like most of the research that we found, they were evaluating the row mechanism in a single row group configuration. It means like we need to identify or to create a new algorithm that can work with multi-row group configuration. So for the modeling of the networking or the IoT networking, we use the NS3 software. And if we, well, you can see at the left side, this is the flow diagram, which indicates a process that takes from the access point to synchronize the station. It means like the access point should give the identifier and assign the right row group and row slot to the station so they can communicate at the right time with the access point, or they can start the content for the channel. Then I have the table with all the parameters that we use for the simulations. I would like to focus on the MAC layer parameters, where if you can see, we use multiple row groups that it went from 1 up to 8 row groups, and also multi-slot configuration that it went from 1 to 4 slots configuration. And we use UDP echo traffic, as we saw earlier before, IoT implementations work with TCP and UDP. Some research that they mentioned that UDP is mostly used for monitoring implementations. So now I would like to show our results. First I should mention that for the set of configuration that we used before, we use a code scheme of index 0 that it allows to reach a data rate up to 300 kilobits per second. That is this is the highest data rate that the channel can reach. Configuration. So if we see here in of configuration, we have a mixed configuration, well, multi-row slot, multi-row groups, and with singles configuration with one row group was slot, it was the highest channel traffic flowing during the simulation. So as we increase the configuration in the row, also in the slots, this channel traffic was decreasing. So it means like the channel was less saturated. This doesn't represent the data rate. I will show later the data rate in the channel, but it is just to have a perspective how we can prevent saturation in the channel by using this row configuration. Then here I have the graphs about, as I said, it's packet loss percentage by also the different row configuration. All these configurations were only with one row slot per row group. So if we see before the 1000 stations working at the same time, there is not such a big difference in the percentage of packet loss. They all remain, all the results remain pretty close to each other. But after we start working with higher number of stations and reach the 2000 stations, we see a higher difference, almost well, it was pretty close to 15% difference from one row group to 8 row groups. So again, we are preventing saturation in the channel so we can get better quality in the communications. Then at the right side, I show the mean data rate and the maximum data rate that we saw during the simulation. And also the trend is pretty the same. For single configurations with only one row group, we reach even, we saturate the channel, but when we increase the number of row groups, we prevent that saturation. Yeah, now supported the statement that preventing saturation can increase or can perform the quality in the communication. At the left side, I have the graph where we show the average number of packets sent from the access point and then average number of successful packets received. If we see in average, there were sent 8 packets by the access point, but the results were different for each configuration. So with single configuration, with single row configuration, we only reach around 2.5 packets received at the other side. But when we increase up to 4 row groups or 8 row groups, we got a result twice bigger. Like we reach almost 5 packets received at the access point, at the station side. Finally, I just want to show the last graph that shows the power consumption per station. For a small number of stations, well, small in terms of how many stations the standard can support, it's before the 500. The difference in the power consumption is pretty, well, there is not such a big difference. But when we start working with higher number of stations, we can see a bigger difference. Actually, the biggest difference is shown in the 2000 stations working at the same time, where the best performance is shown for the 4 and 8 row groups. This is important to mention because in the long term or in a long term application for IoT environments, we can save a lot of energy in the devices, so that we can implement like more independent solutions, so more less energy dependent solutions. So our conclusions were like working with multi-row configurations can improve quality in different aspects of the communication. Like I showed before, we prevent the saturation in the channel. Also, the quality of the communication was bigger because it was twice bigger the number of packets successful at the station side. So we support that even when the row mechanism is being evaluated on different research, we support the idea that deeper exploration of the row mechanism, how it can work, how we can set proper parameters to bring these benefits So the IoT implementation, it could, I mean, like we open the discussion for further investigation. So that's it from my side. Thank you for your attention.
Thank you very much as well. Now, please, space for questions. Anyone interested to ask something? I can't see. Anyway, the same question from me as with the first presentation given by Istvan. If it is possible to see some documentation of your investigation, your research somewhere so that we can share some data or some results?
Well, currently the algorithm that I use for the simulations is still private on my repository. I just have to discuss with my colleague if at some point we will make this public. But yeah, I base almost the algorithm in what is public, what is already public from the NS3 developers.
So again, I'm warning you that I'm going to share this information with my colleagues in the research group, and perhaps we will contact you because it seems interesting and there may be some intersections in the research.
Yes, for sure.
Any other questions or inputs, please, gentlemen? Well, if not, then to follow the timeline, thank you once again.
Thank you.
Please stop your sharing. And I'd like to invite next speaker, who should be Devrim, if I pronounce it correctly. Now we are transiting again to the area of signal processing and image processing. So please let us know what's new in this area. The floor is yours.
Hello, everyone. I hope you can hear me. Okay.
Yes.
Let me share my desktop. Okay, share screen. Where can I find? Okay. Can you be able to see my screen?
Yes, we can see the
okay.
window of your PowerPoint, so maybe it's better.
And this is PDF document. Doesn't matter. Okay.
Then Control-L is the good option. Control-L if it's PDF, but it isn't. Or simply using the presentation mode.
Okay.
Thank you.
In this paper, we presented a machine learning method for detecting the trace of seam carving. And in our work, we developed a machine learning approach for detecting whether image is manipulated with seam carving or not. So seam carving is a kind of image retargeting approach, is a manipulation tool for resizing the image while aiming to keep image distortion at low level. And it is usually, seam carving detection is usually interested in image forensics. And so we applied seam carving, and also we developed an approach to detect whether an image is seam carving or not. In our paper, we developed a machine learning method and compared it with the state-of-the-art studies. And our method involves a stripe-based approach together with local binary patterns transform and energy map and some features. As you know, machine learning approach usually involves extracting features. So we also utilize a support vector machine for classifiers, and we also finally compare our results with the state-of-the-art studies, with the recent studies. First, I'm going to talk shortly about literature. As I said, seam carving is a kind of image resizing, while the aim of seam carving is to preserve the content of the image as an alternative to interpolation or other approaches. Is one of the popular methods in image processing, image resizing applications. So, but in literature, there are also various studies to detect whether an image is seam carving or not. So we checked the literature, And we also developed an alternative and improved method to literature. When we look at the studies, because these are usually machine learning based methods, there are also some deep learning approaches, but we usually interested in machine learning approaches. And we also compared our results with some of the deep learning approaches. I will talk in the conclusion sections. So these machine learning methods usually involves some extracted features such as Markov features, discrete cosine transform, gradient histogram, and the features of SIM carving process, for example, noise features and local binary patterns, local derivative patterns. We also utilized local binary patterns in our study. For example, Weber local descriptors. There are various methods based on machine learning. And there are also convolutional neural networks for this used for this purpose. And as you know, convolutional neural networks extract their features by using the definite layers, and therefore they don't need specifically extracting features, but sometimes specifically extracting features may help you to obtain better results when compared with deep learnings. So first, I'm going to talk what is SIM carving and some basic topics, and then I'm going to talk about our method. A SIM carving, a SIM is described as an 8 connected path of pixels along the top to the bottom or left to the right. So during SIM removal, you can remove SIMs in the horizontal or vertical directions. So SIM carving is a content aware, and it's what do we mean content aware? It doesn't it's with the help of energy map, it usually removes unimported paths, so it helps to preserve the content of the image. But there are some when you remove a lot of SIMs, it also disturbs some content, some objects in the image. But in practice, the aim of SIM carving is to preserve the content of the image. In this method, an optimal is SIM found and removed or inserted one by one until the desired image size and other stepped conditions are satisfied. So it is usually applied with computing energy map or various approaches for this purpose. And then cumulative energy map is computed, and based on this cumulative energy map and the summation of these pixel values helps you to determine the optimal SIM. So there is an example for this. This is the energy map obtained at one of these approaches. And once you compute energy map, for example, here, energy map. Okay, let me find the pencil here. Here, this is the energy map of in image, as you see, and these numbers are cumulatively summed below, starting with the second row. For example, this 80. Okay, this number is summed with one of the smallest pixels, and then this one is also summed with smallest one. For example, this one. As you see, this pixel is a neighbor with these 3 pixels. So this map is, excuse me, let me find the numbers. This map is formed by summing these pixels based on the minimum values, minimum neighbors. So once you obtain this minimum cumulative energy and you check the path, start with the minimum value, minimum number, and find the path with minimum values. we are trying to find the path with minimum values, but at this point we are checking only the neighbors. For example, the minimum value of 75 is 191, and the minimum value of 191 is 301. In this way, this gives us usually the unimportant path of pixels. So this is the application of, this is the main idea of seam carving. So this is an example paths removed from the scene, from the image. This is the energy map. These are the remote paths. And because in our machine learning method, we utilized local binary patterns. Maybe this is one of the basic methods, but I'm going to talk about it concisely. Local binary patterns is usually used for extracting texture features. It's called as visual descriptor, and its features is usually utilized in machine learning applications. The images are generally divided into 3 by 3 cells, or sometimes 5 by 5, but in general 3 by 3 is preferred. And each window, 3 by 3 window, is converted to a binary number by comparing the pixels in this window with the center pixel. For example, in this example, in this for these values, the comparison is start with this pixel, but you can change this. For example, you can use this the first as a first pixel, and in that case, you need to apply this to all pixels. Yeah. In other words, you need to fix the starting pixels for all windows. So once you select the first pixel, you compare it. For example, the center pixel is lower than the neighbor above, then we set it to 1. We set it to 1. And then this one is smaller, then set it to 0. So once all the neighbors are okay, we control them and we form a binary number. And this binary number is the local binary pattern. This is a very useful approach for extracting. Maybe I had better to put here an image, local binary pattern image. It gives us some details of the image. It's very useful for machine learning classification applications. In our paper, our contribution, actually the main contribution here is to provide a better machine learning method. And for this purpose, we used a stripe-based approach. We divided the image into stripes, and we also utilized local binary patterns, and also we utilized some features. I'm going to talk about them, and we also realized that taking the square root of this the emerging map provides better results. So we also take the square root of the energy map, and we called our method stripe-based seam carving detection method. And as I said, we divided the image into stripes and utilized some features such as local binary patterns and some statistical features. So we determined the number of stripes. We checked various number of stripes, and we determined the best stripe. For example, for our case, we used 6 stripes, but here is an example: 2 stripe case, 4 stripe case, and vertical or horizontal. And so this helps us to find, this helps us to improve our machine learning approach for the detection of seam carving, as I talk in the conclusion section. These are the other features. These are extracted from the images. These are some statistical features. For example, maximal value of a stripe, minimum value, horizontal and vertical directions, standard deviations, and differences between the neighbors stripes, and these are the extracted features after local binary patterns. First, okay, excuse me. Here, first we convert our image to gray image from RGB, from color image to gray image, and then we apply local binary patterns, and then we compute energy map, and these are the we also took, especially we show this here because nobody used this in this way. We saw that this is useful to improve the features, and then we divided the image into stripes, and then applied the statistical after minimum cumulative energy map. We applied the computed to scene features. So these features are the features here, statistical features. And according to the number of stripes, the number of features are also increased. And these are used for used as input to our support vector machine. And as a data set, we used UCID data set. We use this because in literature, most of the authors use this data set in order to do a comparison. We use this data set. It contains 1,338 images, and these are 512 by 384, or the rows 384 by 512. So because the level of seam carving affect the detection rate, we used various rates. These are the preferred rates in literature. Also, we forget to write here. We also, because in the papers we saw 40% and 50%, we also used this. And after application of these ratios, our data set becomes 8,000, about 8,028 images. And
sorry to interrupt you.
Excuse me.
We have to do it faster because the time is almost over. So please.
Okay, I'm finishing it.
2 more minutes. Yeah?
Okay.
Thank you.
I am finishing it. This is, as I said, this is our main approach. We processed all the images, and this is the basic idea of our approach. And there are okay, and we did some comparisons here. As you see, we tried 1 stripe, 2 stripe, 4, 6 and 8 stripe approaches. For our case, we found that 6 stripe is good, but because our image is fixed to a certain size, this may differ for higher dimensions. For example, 8 stripe may work on higher resolutions. So when we compare with the state of the art, and we are good at most points except some smaller ratios. For example, 3% scaling is difficult to detect. So a deep learning approach is better than us, but for the other cases, our approach outperforms. So we mistakenly wrote this to the paper because I realized that we also are good at 30%. And so in conclusion, we developed an efficient machine learning approach based on some extracted features, but the recent trend is in various areas is to use a deep learning approach. And we also we are also doing some experiments on deep learning approach, and we obtained good results, but we haven't published it yet. And also another open topic is the localization, such as I saw some approaches like YOLO or other deep learning approaches for detecting the place of seam current, for locating the position of SIM carving. Also, another point, all the literature used fixed size images, and it is necessary to use various size images in various images in various dimensions required to obtain better performances. That's all I want to say. If you have any questions, I can answer. Thank you for listening.
Thank you very much also. Perhaps there is time for one fast question. Please, gentlemen. Since this is not directly my cup of tea, I'd like to pass the word to anyone. If not, then thank you for the moment.
Thank you.
Because of time constraints, I'd like to pass the word directly to Zoran Čiča from Belgrade, and his, again, networking topic concerning IPv6 lookup. So please go ahead, Zoran.
Okay, I'm just a second. Okay, I hope you see the screen. Okay, hello everyone, I'm Zoran Čiča, and I will present this paper about the IPv6 lookup algorithm. I come from the Belgrade University School of Electrical Engineering. So IP lookup is one of the critical routers functions, even for the IP version 4 addresses, but also we expect at some point in the future that IP version 6 will finally become a dominant addresses in IP space. And the problem is that most of the existing IP lookup algorithms are practically adjusted, suitable for IP version 4 lookup tables, but do not scale well for the IP version 6 lookup tables. So there is a scalability issues with the existing IP lookup algorithms. IP lookup practically performs for each incoming IP packet. It searches the lookup table. The search is based on the destination IP address, and based on that search, we determine to where the IP packet should be forwarded, to which output port. And the worst case scenario that IP lookup needs to support is when only the shortest packets are incoming at the input port, because in that case, IP lookup has practically the least amount of time to perform its function. One example is given here: 100 gigabit per second Ethernet link, shortest frames are 64 bytes. So practically IP lookup would have around 5 nanoseconds to perform its function. And it's a very, very short amount of time. So IP lookup needs to be very, very fast. And that is one implementation problem. The other problem is that when we look at the core routers, well, the number of entries can be very large, hundreds of thousands of entries. But on the other hand, the lookup tables should be small, and that is also a sort of scalability issue. The algorithm needs to, make modest requirements for the storage of lookup tables. There are several classes for IP lookup algorithms. One of them is a tree-based lookup algorithm. So this class is very popular because the tree structure represents practically a natural way to store the lookup table. If we look at these prefixes that are stored in this tree, and for example, let's say that our IP address starts with 3 zeros, then we would follow this path. Left branch is 0 and right branch is 1. So we would follow this path. We would find 2 matches, A and C prefixes. And practically, we always choose the longest prefix according to the longest prefix matching rule. And in this case, we would select prefix C as the entry that we want to retrieve, and we would find out to which output port the packet should be forwarded. However, there are 2 serious problems with tree structures. One is the number of empty nodes. Of course, this is very small tree, but in reality, the trees are greater. And the number of empty nodes is very, very large, especially in the IP version 6 case, because most of the prefixes are deeper in the tree from levels 32 to 48. So this means that many empty nodes that do not carry actual information, they are just needed to keep the tree connected, are practically requiring very large memory storage requirements. And the other problem is that Each node is actually, in most of the cases, one memory location. So practically we need to have multiple memory accesses to traverse the tree, and that slows down the lookup process. It would be ideal that practically we have only one memory access per one lookup. So let's see how these problems are solved in the literature. Well, the problem of empty nodes is solved by using so-called priority trees. So what is the story behind the priority trees? Practically, we have some empty node in the classic tree. So we look up to its descendants, find the longest descendant, longest prefix descendant, like G in this case, and we move this information about the G in this empty node. Similar goes for this node. We have two candidates C and F. For example, we move F here, we move E here, and so on. So at the end, we have something like this. This is so-called priority tree, where we have no empty nodes. Of course, the price we pay is that practically we need to store the actual prefix in the node, because now it can be different from the path. It can be longer than the path to that node. But this is justified because there are no empty nodes, so the memory savings are still very, very great. On the other hand, to avoid multiple memory accesses, well, we cannot avoid actually multiple memory accesses. It's natural, but we can sort of use a pipeline, and we can virtually achieve that we have one memory access per one lookup. How is this naively done? Well, it can be done that each level in the tree can be stored in the different stage. Each stage 1, 2, 3, and 4 has its own memory, and practically it stores the nodes from that level. So actually, when one lookup starts, it goes to stage 1. After the search, it follows the path and goes to stage 2, then stage 3, etc. But once this lookup passes from stage 1 to stage 2, new lookup can start at the stage 1. So we can have multiple lookups at the same time, and virtually we achieve one memory access per one lookup. However, the problem with this naive approach is that the memory sizes in each stages are different size, and this is not good for the implementation. It would be more suitable that these memories are the same, and this proposed solution in this paper tries to solve this problem. We proposed here the balanced pipeline lookup. This is the general architecture, and the general idea is the following. The original binary tree is split to subtrees at the split level 16. So selector practically takes the IP address, checks the first 16 bits, and determines to which subtree search should be performed. Then practically search is performed in the pipeline stages. That is where the subtrees are stored. And at the end, we get the solution, the best match that points out to the location in the next hop memory that practically from where we retrieve the next hop information, that is where the packet should be forwarded. Just to note, the subtrees are actually priority trees, so there are no empty nodes. And this significantly reduces the memory requirements. Also, the pipeline stages are balanced. We will see that later. And the memory sizes in each pipeline stage are the same. So this is good for implementation purposes. So this slide shows how this balancing is achieved. Well, practically, the most important thing is that the ancestor node and its descendants needs to be in different stages. And this ancestor node needs to be in the prior stages. That is the only requirement. So we have, for example, also node A. Here it is, it's in stage X, but even though that C, D, E, and F are in the same tree level, they can be stored in different actually pipeline stages. For example, I can be different from the Z. Also, to reduce the memory requirements to reduce actually the number of pointers, this node A has two descendants, C and D, direct descendants. But we place C and D in successive locations, so there is a need for only one pointer that points, for example, to the left child, and we know that the right child is one location above. So in this case, we can easily manipulate the contents of the pipeline stages, and we can easily balance the number of nodes between the stages, so we can have the same memory requirements. And by having the split level 16, we have enough, enough subtrees that we can easily populate in the same way the first few stages to avoid slow starts and less memories in these first stages. This slide shows the architecture of one Python stage. It shows only the lookup part, not the update part. And the main part is actually this stage memory. Stage memory is dual port memory, when one port is dedicated for the read operations that are used in the lookup process, while the other port is used for the write operations that are used for the update process. Practically, this comparator checks whether we have reached the stage of interest or not. If we have reached the stage of interest, that is where the node that we want to inspect resides, then some additional operations will be done. But if we have not reached that stage yet, then all these inputs are simply passed to the output ports until we reach the stage of interest. If we have reached the stage of interest, then this comparator practically compares the prefix with the IP address. And if the comparison is positive, that means we found the new next best match, then this multiplexer will practically pass this new result. Otherwise, if there is no match, the old result would be passed. One location contains two parts, two informations. One information is the prefix, actual value of the prefix, and the second information is the pointer value. And the pointer comprises two parts: location ID, that is the location in the stage memory, and the stage ID, which stage should we look. And the result is actually the pointer, because each location in each stage memory from any stage practically corresponds to one location in the next scope memory. So practically this location plus, that means concatenated with the stage ID, practically represents the location in the next scope memory from where the next scope information is retrieved. This multiplexer practically, when we reach the stage of interest, now we need to check the next node. So this multiplexer selects the new pointer, because now we point out to the next node we want to inspect. Of course, in the network, frequently there are a lot of changes in network topologies. For example, router can fail, links can fail, routers can be added, links can be added, and etc. So routing protocols will frequently update the lookup table. However, the important thing is that update of the lookup table should have a minimal impact on the IP lookup process, in sense to minimally disturb the IP lookup process. So that means actually that the updates should be incremental, and we should avoid to rebuild the lookup table. Also, the update should be fast and simple to fastly follow the network topology changes. This slide shows one example, the most complicated example of the update scenario. I will go briefly just here. We add practically prefix 5, that is the longest prefix in this observed subtree. And to see how the balancing works, currently least popular at that point of time, the least populated stage is, for example, stage 2. So we want to add practically a node in the stage 2 to balance the number of nodes across the stages. But the problem is that we cannot put prefix 5 here, because it's longer than 2, 3, and 4 prefixes. So actually we move 2, 3, and 4 to these prior stages. 2 will move to stage 2, 3 will move to stage 4, and 4 will move to stage 6. And we now in an occupied space can put this prefix 5. However, the most important thing here is that all these calculations are done in the control plane. So actually, this proposed algorithm can go is in line with the software-defined networking, in sense that the control plane and the data plane can be decoupled, and all the calculations are done in the control plane. And actually, control plane just sends to data plane pairs address value, where address is practically the pointer stage ID plus location ID, where the data should be written. And the value is actually data that is written to the tables and to stage memories. And practically based on the calculations, a batch of these pairs address value are sent to the data plane, and data plane just sends it to the pipeline stages. And it's written using that other port in dual port stage memories. At the end, we compared the proposed algorithm with some other tree-based recent algorithms, and we used for the comparison on-chip memory requirements. The reason is very simple, because there is a need that lookup algorithm should be fast. That means that we should have one memory access per one lookup. And that means actually that we need to have multiple memory instances. So the natural choice is to use on-chip memory for these memory instances, for example, on-chip memory on FPGAs. And of course, the other requirement is that these requirements should be low enough to fit the total on-chip memory. Based on this table, we can see that BPL actually has the least memory requirements. And also it can support very well even very large lookup tables. So all the requirements are fulfilled. So as a conclusion, I will just summarize things. The proposed algorithm can achieve very high lookup algorithm, very high lookup throughput, while still having very low frugal memory requirements. And actually this helps to support very large IP version 6 tables. And the plus is that table updates, lookup table updates are very simple and very fast, and they are in line with the SDN principles that are actual today. I hope I was fast enough. So thank you for your attention.
Thank you very much. Once again, I'd like to ask about any questions. Please, gentlemen. Well, perhaps could you please give us an example to have a brighter idea, an example what I could expect from this type of algorithm or technique in a live network, I mean in practical networking applications. So
okay, well, I didn't put it in this presentation because of the time, but well, that depends actually on the size of the table. For the smaller routers, this algorithm is very suitable for hardware implementation. The paper itself has an example of the FPGA implementation, how many resources are used. But the thing is that mainly depends which router we are targeting. If we are targeting the routers that, for example, are on the edges that should not have very large, how to say, memory lookup tables, then these small FPGAs can be used, and it will be a very economic solution. However, if we target the core routers, then we need to use high-end FPGAs, and that can be problematic because they are pretty expensive. But that is the price you pay for the core routers. I mean, core routers need to have, how to say, high performances. So that is just a question about the lookup table size. The logic itself, as it can be seen here, is very simple. So the only question is how many these stage memories and how big they should be. And that is the main question. All the calculations are done in the software, in the control plane, so that is not a problem. This is not, how to say, implementation issue or the resource issue, but these stage memories are critical. So this is the main question, how big the lookup table we are targeting. The bigger the lookup table, that means that the higher end the FPGA chip should be used. But in most of the routers, this is not necessary. So actually, this can be a very economic solution.
So you can see the future in a routine integration with standard network elements and devices.
Yes, we hope that, but we will see, because this is now also the question about the how to say, targeting the producers, because usually producers have their own solutions. So it's a bit tough, but we had the project that is still going on regarding the small routers integration. So we hope we can use it there and we could commercialize that product, but it's very hard to be honest.
Thank you once again. One more time, any questions from anyone else, please? If not, thank you. Please stop your sharing. And I'd like to invite the last speaker in this session, who is from the University of Istanbul. I'd like to pronounce your name, Temel Sunmezocak, right? More or less.
Hello, everybody. Hello.
So please.
Can you hear me actually?
Yes, so we can.
Okay.
although the sound quality is not very impressive, but hopefully it will be at least comprehensible. So please go ahead with your topic concerning, again, medicine and diagnostics and evaluation of signals, please.
Okay. First of all, thanks to your organization to give a chance to present my work. I'm Temel, the PhD doctorate student of the Yıldız Technical University, and also I've been working at the Haliç University as a lecturer. My topic is the detection of the electromagnetic signals by neural networks using autoregression and wavelet entropy for bruxism diagnosis, which had been published in Journal of Electronica last month. Our topic is the introduction and materials and methods that consist of the electromagnetic signal acquisition, processing, and electromagnetic feature extraction using autoregression modeling. And we clarify the electromagnetic feature extraction using discrete wavelet transform diagnosis of the bruxism by neural network classifier. And we will finish the experimental results. Bruxism is a chronic dental problem seen in many people today. Its treatment is difficult, has a low success rate. Bruxism is defined as a perfectional grinding of the teeth and involuntary contraction of the lower jaw muscles. So in bruxism patients, hypertrophy in masticatory muscles, tooth wear, implant fractures, tooth loss, and fatigue and pain in jaw muscles can be seen. These symptoms are due to the application of a force that is very high for the physiological structure by the involuntary contraction of jaw muscles. Recently, studies based on joint analysis of electrocardiography and electroencephalography (EEG) signals, together with surface electromagnetism, have been carried out for the clinical diagnosis of bruxism. However, these methods for clinical diagnosis of bruxism are costly and time-consuming, and they require specialization. For this reason, the golden standard for bruxism diagnosis, especially during sleep, is the evaluation of electromyogram of the masticatory muscles together with audio-video recordings through polysonography in a sleep laboratory or hospital setting. But it's very complexity, and it's a high cost of this method. It's a disadvantage. Therefore, it's crucial to develop practical, efficient, and economical solutions based on only use of electromagnetic signals. So we design an electromagnetic measurement system in the home environment. In the study, to achieve an accurate diagnosis of bruxism economically with only electromyography measurement, an even approach based on the autoregression and channel entropies of discrete wavelet transform energy spectra to identify jaw muscle activities and fatigue conditions is proposed. By using artificial neural networks in the proposed model, bruxism activities can be detected most accurately. Electromyogram signal acquisition and processing we mentioned. The experimental setup used for acquiring data from the subject is shown in this figure. The dual channel data label was designed for surface electromyogram signals to collect from the skin surface. Electromyogram signals received from the skin surface were amplified with the instrumentation amplifier. It's a very high gain. The amplified signals should be free from noise, since the meaningful frequency of the electromagnetic signals obtained from the muscles is within the 10 Hz and 500 Hz range. A second order Butterworth bandpass filter with corner frequency is 10 Hz and 500 Hz was designed in this section. So for the recording of measurements, bipolar electrodes of 50 millimeter diameter were placed on the skin surface over the masseter muscle of the subject with 1 centimeter intervals, and calibration and normalization has been done. Then analog electromagnetic signals are digitized and transferred to PC environment using the prefrontal system. Data received from the subjects are sampled to have 4,500 samples per second. The data are analyzed by using MATLAB software in this environment. As you see, this is the electromagnetic signals of the pulse of the subjects. For example, the A sequence is relaxed, and the B is the muscle is closed or clenching, and the C is the fatigue and pain, and the D is the rhythmical teeth grinding. It's a parafunctional activity. To identify these states, unlike other Bruxism-related studies in the literature, discrete weather transform and autoregression models are used together to extract the most salient features from each electromagnetic signal from these two methods. 20 different parametric coefficients are obtained for each electromagnetic signal of 1 second period. You can see the block diagram of the electromagnetic recording system. Considering that there are 125 different electromagnetic signals collected from each subject, a total of 2,500 data are obtained. The block architecture of the proposed model that outlines the entire study is shown in this figure. You can see. Electromagnetic feature extraction using auto-regression modeling that we mentioned. Auto-regression contains important state parameters of the system and is of great importance for time series analysis since it's very sensitive to time-dependent changes in the system. This model is an important one in terms of capturing the key characteristics of any data set. In this formula, you can see the autoregression model A1 to up to A12. This is the feature. This is the most important parameter. These parameters can be used in feature selection from electromagnetic signals for Bruxism diagnosis as coefficients of order 12 that represent X time series. We mentioned that electromagnetic feature extraction using discrete wavelet transform. This is the two important functions are involved in the application of discrete wavelet transform to an electromagnetic signal. First one is scaling function, and the second is the wavelet function. To decompose the signals into different bandwidths to calculate the coefficients CK in the scaling function and the BK in the wavelet function, it should be passed through a high pass filter and low pass filter shown in this equation, as you see. So we taken the tail components, especially DT and approximation components, using these coefficients. DT is a very important parameter because we use DT to calculate the AG key. EGK, which means channel entropies. It's the very, it's the feature, it's the input feature for the diagnosis of the bruxism. EGK, the tail component, expresses the tail component obtained through wavelet transformation in the frequency domain, depending on the sampling frequency at G and time t. Hence, wavelet channel entropy of each detail component shown in this equation can be calculated easily. Diagnosis after taking the features, both autoregulation and wavelet energy entropies, then we using the neural network classifier in order to classify detected bruxism diagnosis accurately. In the study, autoregulation coefficients and wavelet channel entropy values of the 125 different electromagnetic signals obtained from the subjects for the case of perfectional teeth grinding, jaw squeezing, and the resulting pain or fatigue that occur during bruxism compress the input to the multilayer perceptron. For this reason, two different network structure with respect to the input characteristic of the electromagnetic signals are formed. This structure shown in this figure. In this figure, each data are divided into three groups. Ratio, such as training, validation, and test with respect to input characteristics of the created structure. The number of neurons for the hidden layer was determined as 10 in our study. To investigate the performance of the method used, the classification accuracy was calculated according to this formula. In this formula, here in N is the number of classes, and CCS is the number of correctly classified samples. TNS is the total number of the sample, which was obtained from the convolution matrix. We mentioned that the experimental result can be seen that multilayer perceptron structure with much higher performance can be created when autoregulation and variational entropy parameters. This created structure can be trained quickly with a high performance using Levenberg-Marquardt algorithm. In this figure, the coloration performance of the network according to the input characteristics. Both features is autoregulation and variational entropy is the very high accuracy. As you can see, the performance is 0.98. It's very, very high.
If I can ask you, go right to the conclusions because we are short of time. I'm sorry for this, but we've had a long presentation before you, so please make it as short as possible now. Thank you.
Okay. I know there is no time. I had to hurry up. As a conclusion, this study, unlike other studies in the literature that consider electromagnetic signals for bruxism disorder, jaw locking and random teeth grinding movements are considered together with pain and fatigue in the jaw muscles as a whole. An effective system for accurate bruxism diagnosis is proposed. And also, by virtue of its being based on the design of a system that records on electromagnetic signals in a home setting without the need for a laboratory setting, the study is a practical and low-cost system. Activities that occur during bruxism should be recorded real-time through electromagnetic signals, and the most effective features should be extracted by way of time and frequency analysis. This way, the signals acquired from the EMG measurements can be classified with 100% accuracy by neural network algorithm by using both autoregression coefficients and valid channel entropy coefficients obtained from valid transform of the same signals. With the approach proposed in this study, when the cost and time spent for using only electromagnetic data are considered, its practical method for wearable or portable electromagnetic devices and a suitable approach for the effective use of therapeutic wearable electronic stimulations in the future studies. Thank you for listening.
Thank you very much. So one more last time, questions, please.
I know it's too late, so I hurry up.
I'm sorry for not keeping the time schedule before, and have to make it faster in this very last moment. My question would be: so if I do understand correctly, you assume that the system proposed like this shall be able not only of diagnostics of the problem, but also of therapeutic application. Am I right?
Yes, it's true. This system is very easy to use. System records the data during the sleep, then they convert the digital system in order to detect bruxism in PC environment. All lower jaw muscles activities can be detected in 100% accuracy. Afterward, we're planning to minimize the system for using home environment. Meanwhile, during the sleep, all lower jaw activities is not related to the bruxism. So it's very important thing is to distinguish the meaningful signal for the diagnosis of bruxism.
Yes, thank you very much.
You're welcome.
Gentlemen, thank you for attending this session this afternoon. As I said, we have run almost also of the break between the sessions. So I'd like to thank you once again to conclude this session. Thank you very much for your contributions. As for the questions and discussion, I'll send the emails to some of you, perhaps after discussion with my own colleagues. The contacts are also in the papers, so please feel free to contact each other if you're interested in the results of the other colleagues. And thank you. Have a nice afternoon. And the next session shall start in some 3.5 minutes.
Okay, thank you.
Apologize.
Thank you for all of us, all of you.
Apologies to Darius.
Thank you.
Bye-bye.
Okay, thank you. Thank you for the presentations and sharing as well.
Okay,
See
thank
you.
you, Darius. Bye-bye.
Bye-bye, everyone.